Well, folks, we've made it. The last section that we need to cover, 12.7. This is going to use compounding formulas that are exponentially based. So, our two compounding interest formulas that we're going to look at is compounding interest by with the number of compounds. So, to define this, this is the A is the amount in your account, N is the number of compounds, P is the principal in your account, that's like your beginning balance, and R is going to be your rate, but it has to be given as two decimal places. So if you're given a percent of 4%, you have to change it to 0.04. Our next one is continuous compounding. This is when you're constantly compounding every second of the day, every nanosecond, and you're constantly making money. So A again is the amount in your formula, P is your principal, R is your interest rate written as a decimal, T is your time in years. So looking at an example of how to use these formulas, $8,000, that's your P, is invested at 5%, that's your rate, 0.05. For 3 years, that's your time. What is its future value, using your future value formula, of the account for the following compounds? Now we're going to put in the N. If it's annually, N equals 1. Substitute everything in. Do I really need to divide by 1? No. Do I really need to multiply by 1? No. But what I'm going to do in my calculator, which might be wise for you to do because they usually ask you different number of compounds, is to put it as 8,000 left parentheses 1 plus 0.05 divided by 001. That's still a 1. But this number of compounds, which goes up to daily, means 365. We'll just type over that when we get into when we get to daily. So raised to the power of 001 times 3 is $9,261. Semi-annually, your N is 2. Show me the substitution, then I go to my calculator. So now you can see I've typed over the 1, put in a 2, typed over this one, put in a 2. Everything stays the same. So what I'm doing here is I'm going second enter to bring down the previous statement, and then I edit over the ones with 2's. $9,277.55. We always round it to two decimal places, so 7 rounds up to 4. Quarterly, N is 4. So everything stays the same except the 2 and the power in the denominator are going to be changed to 4's. So again, with your calculator, second enter to get this statement back. This is 002 becomes 004. 002, change the 2 to a 4. It's now $9,286.04. You'll notice that we're making more money. Monthly, N is 12. I put in the 12s, basically where the 4's were. Everything else stays the same. Now when I go to the calculator, again, second enter, bring down this original statement, but now 004, 012. 004, change the 04 to 12. Hit enter, we get $9,291.78. 365, where the 12 were at, is now 365. Copy that same statement, so second enter. Then we change the 012 to 365. 012, 365 times 3. Now we're at $9,294.58. Compounding continuously using this formula. Every time you see continuous, we're going with this formula. 8,000 times e to the rate 0.05 times the time 3. Calculator entry gives me $9,294.67. That's the highest money you can yield. Alright, next example. $8,000 is invested at 5% compounded monthly. How long will it take to double the investment? Well, what I don't want to do is go back here and keep changing the time until I get 8,000 to double to 16,000 over here. So we're going to take this formula. 8,000 is your principal, but we want that to double to 16,000. 1 plus the rate 0.05 over the n12, that's how many times we compound, raised to the 12t power. Now, in order for us to solve for t in the exponent position, you have to get t out of the exponent position. So this base, parentheses, to this exponent has to be isolated. Divide over the 8,000, you get 2. Once this base and the power are isolated, you're going to convert it to a log. This is going to look ugly, but don't panic. All right, this is my base. So log base 1 plus 0.05 over 12. 12t, you go to the other side. 2, you come over and be in the argument with that log. Divide by 12, and now we type this into your calculator. So again, with this one, because it's a big fraction here, I would definitely opt to type it in with alpha, y equals, get a fraction. Math, go to your log base, and we need 1 plus 0.05 divided by 12. Then it's of 2, so 2 in those parentheses. And then what do we divide by? We're dividing by 12. That's what we came up with right there. 13.89. So if we had to round it to a particular year, round it to 1 decimal place, 13.9 years. If they wanted whole years, then we round up the 89 to 14. Okay, bacteria number 123 grows at a rate of 9% continuously. How long will it take until the population triples? A lot of people will always tell me there's not enough information because you didn't tell me what was the beginning population. Yes, I did give you enough information. First of all, 123 doesn't go do anything with the problem. I'm looking at A equals P times E to the RT power. I have the rate. So R will go in as 0.09. But, okay, what's the P and what's the A? Well, do it this way. The easiest principle to start with is a 1. Then I triple 1 to a 3. Now, do I really need to have the 1 there? Nope. I'm going to convert this into a natural log. So natural log of 3 is equal to 0.09t. Divide over the 0.09. This is my calculator entry. So if I went to my calculator here, I could go literally natural log of 3, close the parentheses, divided by 0.09. Enter 12.2 years. That's our final answer. All right, over here, exponential growth and decay. All they're doing is taking this formula and converting it to a function. Now, for whatever reason, they change R to a K. I guess it's for the following reason, is that if there's growth, your K is a positive power. If it's decay, it's a negative power. Anything greater than 0 is positive, anything less than 0 is negative. A sub 0, this is going to be in the account at time 0. That's just like P, your beginning balance. So you can still use this original formula right here. You don't have to worry about memorizing that. So a colony of bacteria grows continuously. That tells me we're using APERT at 4.5%, 0.045. The colony starts with 100 grams. That's your P. Write the function of the growth where N, capital N, is measured in grams and T is measured in days. So N of T equals 100, that's what we started with, times e to the 0.045 t, and then we're going to solve this. Or excuse me, solve this. We're going to use this to answer all the rest of the questions. What is the population in 5 days? Since t is measured in days, we'll put 5 in for t, substitute it in, go to the calculator, 125.23 grams. How long will it take for the population to reach 150? Okay, so N of T, that's 150. So get rid of the multiplication of 100. I divide over the 100. 1.5. 150 divided by 100 is 1.5. Now that base E is by itself, I'm going to convert it into a natural log. The natural log of 1.5 is equal to 0.045t. Divide over by 0.045t. Go to our calculator, crunch the numbers. Natural log of 1.5 divided by 0.045 is approximately 9 whole days. How long will it take for the population to double? Well, from starting at 100, that doubles to 200. And so basically, 200 divided by 100 is now 2. Convert it to a natural log. The ln of 2 is equal to 0.045t. Divide over the 0.045. Go to your calculator, type it in, and this comes out to be approximately 15.4 days. Next example, 1,000 grams of radioactive material decays continuously. That's our A equals P times e to the RT power at a rate of 11%, so that'll be 0.11. How much is left in 3 years? Okay, so A equals 1,000 is my beginning balance, times e to a negative rate, negative 0.11, times 3 years, calculator entry. Gives me 718.9 grams. How long until there's 300 grams left? We'll put 300 in for the A. Again, we have to get E by itself, divide over the 1,000, which is going to turn into 0.3. Change this into an ln. ln of 0.3 is now equal to negative 0.11t over here all by itself. So let's divide over 0.11 to get t by itself. We'll go to the calculator here. ln of 0.3 divided by negative 0.11. Enter 10.95 years or 4 years or approximately 11 years. Okay, gotta get my calculator off that main screen there. Gosh, dang it, quit moving around. There we go. Okay. Next example. A city has a population of 2,050 people in 2000, and in 2010 the population is 5,215. What is the rate on a continuous exponential function? All right. Here's my A equals P times e to the RT. We're looking to solve for R. So we're going to put something in for capital A, capital P, and the time. So P, that's your beginning balance, 2050 in the year 2000. In 2010, your ending population, okay, that's your A, 5,215. And when I subtract the years, my time is 10. So I substitute this in. 5,215 equals 2050 e to the r times 10. R is the only variable left over in the equation. We can solve for it. So divide over the 2050. Now we're going to convert it to a natural log. And if you want to keep the numbers the same, that's okay because it's going to be a calculator entry. That's the natural log of that fraction is equal to 10r, your exponent. Divide over the 10, and that's what we're going to punch into our calculator. So the natural log of 5215 divided by 2050. Then I have to divide that whole thing by 10. And 0.09336999295. That's my answer. And we'll round it to wherever they tell us for decimal places. Write out the new exponential function. So r goes in as 0.09337 times t. 2050 is our beginning balance, and we'll put a back out in front. What is the estimated population in 2013? Since we started in 2000, that's when t equals 0. 2013 is 13 years later. That's t equals 13. Put 13 in for t of our formula. Crunch this all into the calculator. We get 6,901. And I rounded this to the nearest whole number. And that wraps up 12.7.